Hey, it's Clinkerman again. We are finally at the end of section 7.6, in which we're going to do something that I think is kind of fun. It's also an inexact science, but still entertaining nonetheless. What we're going to be doing is we're going to be analyzing the relationships between the graph of a function and the graphs of its first and second derivative. Alright, now what we get to do here is we get to apply some super reasoning skills. Just based on the things that we know the first and second derivative of a graph tell us about that particular graph. Alright, now I want to start off with a graph of a first derivative of a function and the graph of a second derivative of a function on the next example. And I want to talk about what they indicate about the function. What can you learn about the graph of f of x if you see the graph of f prime of x, as in this example here? It says that the graph of the derivative of f is shown. Okay, so that is f prime of x that's shown. And what these directions want us to do is to write down the intervals on which f is increasing and decreasing. And I'm going to take it one step further, and I'm going to try to figure out where would the graph of f of x have a maximum value and a minimum value if it has either one of those. Alright, well, quite simply, what we're wanting to look at is this. Remember that if the first derivative of a function is positive, it means the function is increasing? Well, there are two places on this graph where the first derivative is positive. Now you have to separate what your eyes are seeing from what you understand. If the first derivative is positive, what that's telling you is that that function is increasing on those intervals. So, when it's asking where is f of x increasing, well, the first place it's increasing is from negative infinity to negative 2. And the second place that it's increasing, ignore that little mark right there, is from on the interval from 4 to infinity. And as you might guess then, when the first derivative is positive, it shows you that the graph of the function is increasing. That when the first derivative is negative, as it is on that highlighted part right there, that means the graph of f of x is decreasing. So if I wanted to say where this function is decreasing, you can see that on the interval from negative 2 to 4, the graph of the function would be decreasing. Okay, now I said I was going to throw in a couple other things that these directions didn't mention. Remember that when the first derivative is 0, that tells you a critical value of a function. And there are two places, right here and right here, where the first derivative is negative. And so you have critical values at x equals negative 2 and at x equals 4. And then if you notice when the graph switches from increasing to decreasing and vice versa, you can tell where the maximum and minimum values occur. At x equals negative 2, the graph is switching from increasing to decreasing because the first derivative is switching from positive to negative. And so if you switch from increasing to decreasing, that means the graph would go like that. You're going to have a relative maximum at x equals negative 2. Now without the actual equation of the function, we can't determine what its y-coordinate is, but we know there's a relative maximum there. And similarly, when x equals 4, the function switches from decreasing to increasing because the first derivative switches from negative to positive. Well, if you switch from decreasing to increasing, that's like this. That's going to be a relative minimum value at x equals 4. Alright, hopefully that makes some sense. Now let's look at what the graph of the second derivative can tell us about the graph of a function. And indeed, you're going to see here, according to the directions, that it says this time the graph of f double prime of x is shown. The graph of the second derivative of f is shown. And it wants us to write down the intervals on which f is concave up and concave down, and give the x-coordinates of any inflection points. Alright, well, Here's how that works. We're again looking to see where this graph is positive and negative. The second derivative of this graph is positive on two different intervals that I just highlighted right there. And whenever the whenever the first derivative, or the second derivative of a function is positive, that means that the function is concave up on those intervals. So, we're talking about concavity here. This graph would be concave up on the interval from negative infinity to 4, as well as the interval from 4 to infinity. I meant to negative 2, this first one. From negative infinity to negative 2, it's concave up, and from 4 to infinity, it's concave up. Now, this is the exact same graph we were looking at a moment ago, but this time the directions are making it the second derivative. Hopefully that's not too confusing for you. Alright, and then a function is going to be concave down anytime that its second derivative is negative, and you can see here on the interval between negative 2 and 4 that the second derivative is negative, and so that means the graph would be concave down on that interval from negative 2 to 4. Alright, and then finally it says to give the x-coordinates of any inflection points. Well, remember that an inflection happens when the second derivative equals 0 and the concavity of the graph changes from negative to positive or vice versa. Well, we have the two places where the second derivative is equal to 0, and the concavity does change at each of those locations. So we're going to have a point of inflection at x equals negative 2. Now that's when the concavity would change from concave up to concave down, because the second derivative is going from positive to negative. And so concave up to concave down would look something like that if we're actually trying to sketch the graph of the function. And then it's also going to have a point of inflection at x equals positive 4, where the second derivative changes from negative to positive, which means that the graph would go from concave down to concave up, kind of like that. Alright, now we're going to go a step further with this. Look at the next example. What this example says is that the graph of f of x is given, and it wants us to sketch the graphs of f prime of x and f double prime of x. It's kind of using the same thought processes that we were in the previous two examples, but a little bit in reverse. Alright, we're looking at this function and we want to draw the graph of its first derivative to begin. Let's work on the graph of f prime of x. Well, there's lots of things that we need to consider here. I think the easiest place to start when you're trying to analyze a graph of a function in order to figure out what the graph of its derivative would look like is to find the places where the first derivative would be equal to 0. Okay? And, well, that's anywhere the slope of a tangent line would be 0 or it'd be a horizontal. And you ought to be able to tell that there are two places here and here where the first derivative of the function would be equal to 0. So since we're trying to graph the first derivative, here's what I'm going to do. I'm going to put a point at 1, 0, because that's going to represent the value of the first derivative at x equals 1. And at x equals negative 1/2, I'm going to put another point in the x-axis, because that's where the first derivative is going to be 0 again. Alright, and then remember we're looking at where is the graph increasing or decreasing, because if it's decreasing, as you see on the first interval, right there, that tells you that the first derivative is negative. Alright, here's another interval where the first derivative is negative. And wherever the graph of the function is increasing, which happens to be the case between those two places where the first derivative equals 0, that means the first derivative is positive. Okay, so listen to my logic here, and I'm sketching the graph of the first derivative. And it doesn't have to be exact, but it does have to keep those qualities that we just described in mind. Alright, so until we get to the first place where the first derivative equals 0, the first derivative has to be negative because the function was decreasing. So there you go, I've got a negative graph until I get to that first place where the first derivative is supposed to be 0. And then the function switches to increasing, which means the first derivative becomes positive. but we're approaching a place where the function is going to switch from increasing to decreasing. We're approaching a relative maximum value. And so the first derivative is going to start getting less positive until it reaches a point where it's equal to 0. And then the function becomes decreasing after that. And so the graph of the derivative is going to be negative at that place. There's the graph of f prime of x, just based on where the first derivative was equal to 0 and where it was positive and where it was negative. Now, it doesn't matter if you get the graph as high or low as it actually would be. It's just the shape. Did you get it positive in the right places and negative in the right places? One more thing. You might be able to tell that the graph of y equals f of x was a graph of a cubic function because it had 2 turning points, or at least we think that it was then. And so it makes sense that the graph of the first derivative would be a quadratic function because the derivative of a cubic function is quadratic. Okay, I'm going to change this picture up a little bit. Or rather, I'm going to just erase everything except for the graph of the first derivative. And now what we're going to do is we're going to talk about how you create the graph of the second derivative. And there's 2 options for this. I'm going to continue looking at the graph of the original function to determine what the graph of the second derivative would look like. Although it's possible to find the graph of the second derivative using the same method that we just did to find the first derivative, but applying it to the first derivative. Alright, I'll show that in the next example. But let's look back at f of x. Again, we would like to know, although we're talking about the second derivative this time, where is the second derivative equal to 0, where is the second derivative going to be positive, and where is the second derivative going to be negative. And I'd like to talk about where is it going to be equal to 0 first. Well, in order to figure that out, we've got to know where is the graph switching from concave up to concave down. In other words, where is there a point of inflection? And if you look at this graph, well, it's concave up on this first interval, and then it's concave down afterwards. And right at the point where it changes from concave up to concave down is where we would say the second derivative is equal to 0, or there's a point of inflection, and that looks like it's at x equals 1/2. So I'm going to put at x equals 1/2 a point on the x-axis to represent where the second derivative is going to be equal to 0. Okay, now on that interval where the graph is concave up, that interval from negative infinity to positive 1/2, the second derivative has to be positive there. Now make a note here. The second derivative was a quadratic function, right? Because it was a parabola. Sorry, the first derivative was. That means the second derivative is going to give us a linear function. Alright? There's the second derivative positive until it gets to the inflection point. And then it switches from concave up to concave down, which means that the second derivative is now going to be negative. Alright, there's the graph of the second derivative of x. Alright, pretty cool, right? One more example. And here what's going to happen is we're going to be given the graph of f prime of x. So we're given the graph of the first derivative, and we're going to use that to sketch the graph of the original function f of x and the second derivative of x. Let's start with f of x. And if we're going to analyze the graph of the function using the graph of its first derivative, we have to see where is the graph increasing, where is it decreasing, and so forth. And we learn that by where the first derivative is positive and where the first derivative is negative. So right here where the first derivative is negative, that means the graph will be decreasing at that point, and it'll be decreasing again once we get to x equals 1. And in between that, where the first derivative is positive, well, that's where our function is going to be increasing. And then finally, there was a point here where the first derivative is equal to 0. Excuse me, that's not the point where the first derivative is equal to 0. There are 2 points where the first derivative is equal to 0. Right here and right here, the first derivative is equal to 0. Now, you see how the derivative goes from negative to positive? That means that this is a relative and negative to positive. That means the graph goes like that. That's a relative minimum value where the function will go from first derivative being negative to positive. And right here, the first derivative changes from positive to negative, and so you're going to have a relative maximum value. Okay, so here's how we're going to approach this. Here where we think the function is going to have a minimum value, where we know it will have a minimum value, I'm just going to put some kind of point that we're going to say that's the lowest our function is going to go. That's arbitrary as to how high or low it goes. There's no reason that has to be negative, but it is going to be a minimum value on a graph. And then right here at x equals 1, where we know our function has to have a relative maximum value, because the derivative changes from positive to negative, well, I'm just going to put a point somewhere that will reach the that will represent the maximum value of our function. All right, and watch this. Remember, wherever the first derivative is negative, that means the function f of x is decreasing. So I'm going to make the graph decrease until it gets to our relative minimum value, at which point the first derivative changes to positive, which means our graph has to change to an increasing graph until it reaches x equals 1, where the first derivative is 0 again, and then the first derivative switches from positive to negative, which means that our graph is going to turn around, and we're again going to have a decreasing function over that interval. All right, so there's the graph of f of x. And now we're ready to graph the second derivative of x. Now I'm going to write something down on the right side of your screen, and I want you to pause to consider it once it's written down. And you see that I wrote that f double prime, the second derivative, is to the first derivative, as the first derivative is to the original function. Okay, now here's what I'm about to do. I'm going to use the graph of f prime of x to try to make the graph of f double prime of x. I'm going to use the first derivative to make the graph of the second derivative. But it's going to be just like I had the graph of the original function. I was trying to make the graph of the first derivative. That's what that analogy is about. So, wherever the graph of f prime of x, the first derivative, is increasing, which you see is right there, what that's going to tell you is that the second derivative is going to be positive there, because the first derivative is increasing over that interval. Alright, hopefully you can see that 0 there. Since the first derivative is increasing, that means the second derivative must be positive. Alright, then, over the rest of the graph of f prime of x, right here, the first derivative is decreasing, which means that the second derivative has to be negative at that place. And then finally, right there where the tangent line of the first derivative is horizontal, well, that's where f double prime, the second derivative has to be equal to 0, because it is the tangent to the tangent, so to speak. Okay, now I'm going to relate this back to the original function in a moment, so if that didn't make a lot of sense, don't worry, I'll tie it in. But let's go ahead and graph the information that we know, starting with where is the second derivative 0, and the second derivative is equal to 0 at the maximum value for the first derivative, which is about negative 1.5. So I'll put a little dot there. Up until that time, the second derivative was positive. And then afterwards, that's when the second derivative is negative. There you go. Looks much like the previous example, for much different reasons though. Okay. Now, just in case what I said about using the first derivative to make the second derivative, if that didn't make sense, let's compare the graph of f of x to the second derivative graph that we made. The f of x was concave up all the way from negative infinity to negative 1.5, and so that's where the second derivative has to be positive, and you can see that that is true right here. And then there's a point of inflection, and so that means the second derivative is equal to 0 afterwards, which you see, we said that right there. And then after that point of inflection, the graph of f of x was concave down the rest of the way, which corresponds with our second derivative being negative. There's how you look at the relationship between the graph of a function and the graphs of its first derivative and second derivative. Pretty cool, right? I'll see you later.